Have you ever stopped to think about what connects, well, almost everything? The food you eat, the plastics you use, even you. At the very heart of it all is the element carbon. But here's the crazy part. A tiny, tiny difference in how carbon atoms link up can change everything. It's literally the difference between solid butter and liquid oil. Today, we're going to dig into why that one little bond matters so much. So that's our big question, right? Saturated versus unsaturated. You hear these words all the time, especially when it comes to food. But what's the actual deal? It sounds like a super technical detail, but as you're about to see, this single difference in a chemical bond completely flips a molecule's shape, its stability, and how it behaves out in the world. All right, so first things first, why are we so obsessed with carbon? What makes it the star of the show? Well, its secret superpower is its amazing ability to form really strong, stable bonds with itself and with a whole bunch of other elements. It's like the ultimate Lego brick of the universe, building millions and millions of different compounds. So how does carbon pull this off? It's all about sharing. See, a carbon atom has 4 electrons in its outer shell that it's ready to share with other atoms. And when they share, they create these incredibly strong connections we call covalent bonds. You can think of it like a really firm, stable handshake between 2 atoms, a bond that's built to last. Okay, this brings us to the first character in our story, the saturated compounds. I want you to think of these guys as the calm, stable, totally content members of the carbon family. And here's the one thing you have to remember about them. A compound is saturated when all its carbon atoms are linked up with only single bonds. That's it. Just one connection, one shared pair of electrons between each carbon and its neighbor. And because they're only using those single bonds, it means they can hold on to the absolute maximum number of hydrogen atoms possible. They are literally saturated with hydrogens. They're full. This neat arrangement gives each carbon atom this stable 3D pyramid shape. Chemists call it tetrahedral. And all of that makes the entire molecule really stable and honestly not very reactive. It's happy just the way it is. So let's lock that in. A saturated compound, only single carbon-carbon bonds, and it's packed to the brim with hydrogen atoms. It can't hold any more. It's stable, it's full, and it doesn't really feel the need to go out and react with other things. But what happens if we mess with that perfect, stable setup? What if we start, pulling some of those hydrogen atoms away? Well, that's when carbon has to get creative, and things get a whole lot more interesting and reactive. Okay, watch this. We start with ethane, a classic saturated molecule. Now let's just pluck off 2 of those hydrogens. Uh-oh. Now each of those carbon atoms has an electron that's looking for a partner. To fix this and stay stable, they form a second bond between them. And bam, we have a double bond. The molecule is now unsaturated, because hey, it could totally hold more hydrogens if it had the chance. Now this is where it gets really mind-blowing. That one little change, from a single to a double bond, completely changes the molecule's shape. It goes from that 3D pyramid structure to being totally flat or planar. And if you go one step further and form a triple bond, the whole thing snaps into a perfectly straight line. The type of bond literally dictates the entire geometry of the molecule. How cool is that? And that brings us to our official definition. An unsaturated compound is just any carbon compound that has at least one double or triple bond. They aren't holding their max capacity of atoms, and that makes them fundamentally different. They're not content and stable, they're ready for action. So what does ready for action actually mean when we're talking chemistry? It means they can do this special kind of reaction, an addition reaction, that their saturated cousins just can't pull off. You see, that double or triple bond isn't just a couple of lines on a drawing. It's a dense cloud of electrons just buzzing with energy. You can picture it like a glowing, high-energy hotspot on the molecule. It's way less stable than a single bond, which means it can be broken open pretty easily to let new atoms join the party. And we can see this play out perfectly in a process called hydrogenation. Here, with the help of a catalyst, we can break that reactive double bond, the molecule kind of opens up, and 2 hydrogen atoms can snap right into place. And just like that, our restless, unsaturated molecule becomes a stable, saturated one again. It's a total transformation. Okay, I know this has been a lot of molecules and bonds, and it might seem a bit abstract, but you actually deal with these 2 types of compounds every single day, right in your own kitchen. Let's bring this all back to food. Here it is, plain and simple. On one side, you have animal fats, like butter or lard. These are typically made of long, straight, saturated carbon chains. Because they're so straight, they can pack together really tightly, and that's why they're solid at room temperature. But on the other side, you've got vegetable oils. They're made of unsaturated chains, and those double bonds create kinks and bends in the chain so the molecules can't pack together neatly. That's why they stay liquid. And this is the real punchline for our health, isn't it? Because those straight, saturated fat molecules can pack together so well, they're also more likely to pack together and build up inside our bodies. And that's exactly why our source material here points out that unsaturated fats, with those kinky chains that don't stack well, are generally seen as the healthier choice for cooking. It is literally chemistry on your plate. So there you have it, from a single bond between two tiny atoms, all the way to the choice between butter and olive oil for your pan. It all comes down to structure, stability, and reactivity. Now that you know the chemistry behind it all, the real question is, are you ever going to look at your food the same way again?